Hello everyone, welcome to the lecture series on IC applications. Myself Sivaramakrishna, Department of ECE. In this lecture, we are going to continue the discussion on characteristics of operational amplifier. And these characteristics are nothing but DC this time. We are going to study and understand the DC characteristics of operational amplifier. The session includes the discussion on bias current, input bias current, and then we will discuss offset voltage, and then it is going to be thermal drift. These are the three characteristics. These are the three DC characteristics we will get a familiarity, or we will familiarize in this lecture in the context of operational amplifier, or in the context of op-amp. So in the previous lecture, if you remember, we have a discussion on AC characteristics of operational amplifier. What are the AC characteristics of operational amplifier? A general phenomena. That is, we input the sinusoidal input, we input the sinusoidal wave, and see the nature of the operational amplifier. That is, the most important parameter is nothing but the frequency response. So why we discuss the frequency response again in op-amp? If you remember, the operational amplifier consists of differential amplifier. In the first few stages of op-amp, that is, the block consists of differential amplifier. So operational amplifier is not too different from any other amplifier. It is also an amplifier having a differential amplifier as the key circuit component in the operational amplifier block diagram. In that context, we studied the frequency response characteristics of the operational amplifier. And coming to the DC, what are the DC characteristics of any device or any circuit? Let us say circuit. If I consider an amplifier, let us say, what are the DC characteristics of this circuit? What are the DC characteristics? I want to study the DC characteristics. What are the DC characteristics present in this? What DC characteristics are DC components? Are DC parameters associated with any amplified circuit? If you remember, the basic amplified circuit, or coming to the differential amplifier, what are the DC components present in the amplified circuit? The question will answer, right? What is the answer for this? DC components are present in the amplified circuit. The immediate answer is nothing but the bias. That is, the biasing components present in the circuit. The biasing components present in the circuit are nothing but the DC parameters. What are the biasing components? We will say that VCC, and another one is nothing but VEE, because we have differential amplifier in the operational amplifier. This differential amplifier is going to have two biasing voltages. What are they? One is the positive bias. We said this is the positive bias, and VE is nothing but the negative bias, right? So this bias produces some current, nothing but the biasing current. Because of this biasing voltage, there will be some current, nothing but the biasing current. I will say this as I, right? So this is the important parameter under DC characteristics of operational amplifier. So what we are going to discuss here, I, nothing but I bias. we are going to discuss the biasing currents or the biasing components. Nothing but the currents. The current components associated with the operational amplifier we are going to discuss. And the next one is the offset voltage. So VOS, the offsetting voltage, VOS we are going to see. And the next one is the thermal drift. The term thermal, what do you understand? What will you say about the thermal? Thermal, if you, the moment you coin the term thermal, you will realize that it is related to temperature. Thermal means temperature. What is the effect of temperature on operational amplifier characteristics or the functionality of operational amplifier? Is there any change? Is there any change in the operation of the device? Nothing but IC. Here device is nothing but the IC, because this IC is also available in the form of a single device. So we can call it as a device. But generally, do remember, device means a diode transistor. Since the entire thing is available in the form of a single package, no problem, you can say that, right? So what is the effect of temperature in the functionality of operational amplifier? Is there any deviation? That's what we are going to say. Thermal drift. Drift means change. What is going to change in the operational amplifier? What will you change? What will change? See, if you consider any device, there are only two parameters. What are they? One is voltage, and another one is nothing but the current. If you consider any electronic circuit, fundamentally it is all about the voltage and currents associated with the circuit. And these two parameters may appear as input and output. That means you will have input voltage, input current, and you will have output voltage as well as output current. Because of the change in temperature within the IC, is there any drift? Is there any drift in terms of the voltage and currents associated with the operational amplifier? That is nothing but the thermal drift, right? First, we will start with the bias currents. See, we know about the op amp. We have seen the symbol for operational amplifier, right? So what it has fundamentally, of course, it is a 7-pin IC, of which these 5 are very, very important, because these talks about these 2 pins represents the input, and this is regarding the output, and this is bias, and this is also biasing. So here we will say this is bias 1, and this we may say bias 2. This bias 1 and 2 are nothing but positive bias, and other is nothing but VEE, right? Now here, where is the focus for bias current? I am talking about the bias current. I said this is the input bias current. Since the operational amplifier has 2 input terminals, namely, what are the 2 terminals? We can say that non-inverting terminal, and the other terminal is nothing but inverting terminal. Non-inverting means this is carrying plus V, and this is carrying some negative. That is, non-inverting terminal will carry a signal of positive, will carry a signal with the positive polarity, and the inverting terminal will carry a signal with the negative polarity. So you can understand these 2 terminals in that way also. So what we are going to say, this op amp having 2 input terminals. This has 2 input terminals. One is the inverting terminal and the other is non-inverting terminal. The signal through the non-inverting terminal will carry a polarity of plus, and the signal through inverting terminal will carry a polarity of negative, right? Since there are 2 inputs, I can say that this is V plus, and I can say this is V minus, Because of this V plus, this will cause some current in the terminal, and because of this inverting voltage, this will cause some current in the inverting terminal. That we may call it as IB plus, and this we will call it as IB minus. What is IB plus? This is the biasing current present in the non-inverting terminal, and IB minus is the biasing current present in the inverting terminal of your op amp, right? So further we can say that the op amp input is made up of differential amplifier, which can be made of BJT and FET. So this is again going back to the fundamental or basics of the operational amplifier. So if somebody asks you what it consists of, what is there inside the operational amplifier? See, this is the very beginning or fundamental IC we can say. Made up of differential amplifier, and these amplifiers are designed by using either BJT or FET transistors only. So we said it requires two transistors, not single transistor. If you remember your basic common emitter or common base or common collector, we can design the circuit using one transistor. Whereas a differential amplifier, we need two transistors. These two may be of BJT or FET. And the base current. What is base in transistor actually? See, base means we are talking about the BJT. So in BJT, suppose you design differential amplifier using two number of BJTs. Using two number of BJTs, we design the differential amplifier. Each transistor consists of what? A transistor consists of basically, it consists of three terminals, right? What are the three terminals? One can say that base, this is your base, and this is collector, and we can say this is your emitter, right? These are the three terminals of the transistor, and here we are saying the base. We know that the transistor consists of three terminals. What are the three terminals? Base, collector, and emitter. Now we are going to specify the current is nothing but the base current. What does it mean? This is the current through the base terminal. The current through the base terminal. Even if you remember, the notation provided here is IB plus and IB minus. What is IB plus and IB minus? What is IB plus? This is the base current. This is the base current across the non-inverting terminal of op amp, and IB minus is the base current across the inverting terminal of the operational amplifier. That is the base currents entering the non-inverting and inverting terminals. So are usually denoted as IB plus and IB minus. If you say IB plus means this is the base current associated with non-inverting terminal, and the current associated with the inverting terminal is nothing but IB minus. Right? Fundamentally, we focus on the base currents, which is due to the biasing, and they are called as biasing currents. The amount of IB in any transistor, the amount of base current IB may vary. It depends on one factor. It depends on the factor of VC's biasing voltage, no doubt, right? So where constant as no current, initially we assume that they were constant as no current is drawn from the input terminals. As no current is drawn from the input terminals, this is true for a given ideal op amp. This is true for a given ideal operational amplifier. Condition, there is no current drawn across the input terminals of operational amplifier. So what you can understand out of this, there are two biasing components. There are two biasing current components in the op amp. They are IB plus and IB minus. IB plus is the current associated with non-inverting terminal, and IB minus is the current associated with inverting terminal of operational amplifier, right? And do you think IB plus and IB minus are exactly same? May not be. See here, are not exactly equal despite the fact. What is the fact associated with this? Both transistors are ideal, are symmetrical, right, are sincerely same. However, the currents IB plus and IB minus may not be same. IB plus as well as IB minus may not be same. Even though you consider or design with the help of two identical transistors, these two current components may not be same, right? Why? What is the reason? Because an inherent imbalance between the two inputs. Do you remember this one? This is a general question. Since I have a single operational amplifier, my biasing is also same. The same VCC and VE are applied to the same operational amplifier. In spite of that, the biasing components may vary. This is because of the inherent imbalance between or within the device, right? The input bias current IB is decreased by, it may vary, it is not decreased actually, it may vary. The input bias current may vary depending on the transistor, the way we design the transistor. That's what we can say manufacturer efforts, how the transistor is designed, right? Now look at the basic circuits here. So this is what the basic op amp, what we said here. You can understand IB plus, IB minus. IB plus is the current through the non-inverting terminal and IB minus is through the inverting terminal of the op amp. And this is the basic circuit configuration to understand this concept. So what we can see here, see the non-inverting terminal of operational amplifier is connected to the ground. It is connected to the ground. It is earth. That means there is no excitation or active signal associated with the non-inverting terminal, right? What about the inverting terminal? There is excitation. There is the excitation or active source that is connected to the inverting terminal. If it is happened so, the circuit is called as inverting amplifier. The circuit is called inverting amplifier because out of the two terminals, the non-inverting terminal is connected to the ground. This is called ground or earth. There is no active source or excitation across the non-inverting terminal. Whereas there is active source connected, which is connected to the inverting terminal of the operational amplifier. If the op amp is designed in such a way that we can understand that it is operating as a inverting amplifier, right? And here, see, initially you may start the operation with Vi equal to 0. Vi equal to 0 means this inverting input itself is at 0 volts, right? And now, of course, biasing is active. Biasing terminals are still active. VCC and VE are still available. I am talking about the input. I am not talking about the bias. Bias is here and this is talking about the input. Because of this input, there will be an active bias current across the inverting input terminal, that is called IB minus, right? So to understand the circuit configuration for base bias currents such as IB plus and IB minus, one should need to provide the input excitation. So it may be your inverting input or non-inverting. Based on that, we can call it as a inverting amplifier or it can be your non-inverting amplifier. Since here excitation is connected to the inverting terminal, we will call it as a inverting amplifier. Whereas the non-inverting terminal is directly connected to the ground. There is no active source available to this. However, because of this excitation, both IB plus and IB minus do exist, right? See, and now I am going to introduce the term called compensating resistance. What is the need of this R comp? Nothing but compensating resistance what is the need of this compensating resistance? Why we need to consider this resistance? If you look at the original circuit, this is my original or actual circuit, and in the next circuit we introduce the compensating resistance which is connected across non-excited terminal. Among the two, which is the non-excited terminal? Non-inverting terminal is non-excited. Non-excited means the terminal which do not possess any active source. The terminal which do not possess any active source. Here I am going to introduce the compensating resistance. Has been introduced or inserted between the non-inverting terminal and the ground, right? That you can see clear here. The purpose of this kind of introduction of compensating resistance is to balance the both biasing currents, IB plus as well as IB minus. Don't think IB plus is very high and IB minus is 0. This will never occur in the operational amplifier. However, the one of the input terminal is ground, that will never affect the biasing current of the corresponding terminal. There will be some amount of current through the terminal which is connected to the ground, right? To balance these two current components, we introduce this compensating resistance. Okay, to see, if you apply some KVL expressions, you can see the analysis. What we are going to see here? See, current IB plus. What is IB plus here? This is the positive biasing current. This is positive bias current, which is present across the non-inverting terminal, right? Because of the R compensating resistance, we can experience some amount of voltage. And let us say this output voltage, the output voltage V0, whatever we specify here, it is fundamentally the difference between the two inputs. It is fundamentally due to the difference between the two inputs. What are the two inputs here? We can say the two inputs are nothing but V2 minus V1. V2 and V1 are the two basic inputs applied across the two input terminals of the operational amplifier. So one can determine the expression for R comp. It is a designed value. The compensating resistance is a designed value. It purely depends on the amount of output which we are expecting, right? Also, this compensating resistance will affect the biasing current IB plus across the non-inverting input terminal. Do remember, the compensating resistance is connected at the non-inverting terminal. So this R comp, the compensating resistance will affect the base biasing current, that is IB plus, which is given by V1 by R. That is the general notation. The biasing current through this, it is usually V by R. The current is equal to, so what is the expression for I? We know that it is V by I, and what is, current is I is equals to V by R. Yes sir. So how many inputs are there? Only one input. We will say that V1, because the other input is connected to the ground. The other input V2 is connected to the ground. Once again, look at it here. So if I say this is V1 and this is V2, there is no active V2. This is generally 0, right? Now the amount of this biasing current, the amount of base bias current across the non-inverting terminal is still depends on the input voltage V1 by the resistance associated with the terminal, that is R comp, right? Compensating resistance. See, voltage present at the nodes. How many nodes are there here? Two nodes. One is A and other is B. So A represents the node voltage across the inverting terminal, and other is anyway 0 because there is no active voltage across the non-inverting terminal. So V2 is 0. So A is a node which is carrying a voltage of minus V1. This is a voltage connected at the or available at the inverting terminal of the operational amplifier, right? So if VA is 0, so we have seen in the circuit, we said VA equal to 0. What is the meaning? It is in the very beginning or the initial states of the inputs or source. If VA equal to 0, so what will happen generally? What will happen? So both V1 and V2 are ideally at 0. That is what they understand. V1 and V2 are 0 because there is no active or excitation across the two terminals. Then we can realize I1, I2, the two currents across the two terminals, inverting and non-inverting terminals, as V1 by R1 and V2 by RF, right? Where RF is nothing but the feedback resistance. Okay, so V0, the output voltage V0 should be the difference between V2 as well as V1. So if VA equal to 0, so see the case here. This is like a case study. So what we are going to say, in the very beginning of the input voltage at the inverting terminal, if you set this at 0, if this becomes 0, V0 should be 0. So because we said V0 equals to V2 minus V1, V2 is already at earth or ground, and in the very beginning V1 we said it is 0. So in that situation, the output voltage V0 should be 0. The output voltage V0 should be 0, right? So what we can say here, so V2 follows your V1 because see what we said, V0 is equal to what we said, V2 minus V1, right? And V0 is also 0 because both V2 and V1 are at 0. V1 equal to 0 and V2 equal to 0. In that situation, one can take this V1 to other side. We can say that V1 is equal to V2 in the very beginning. That means if you set the available input voltage at the inverting terminal is also at 0, you can draw the conclusion that V1 equal to V2, right? See, if that is the case, I can do right as I2 is equals to V1 by RF. Actually what we said, I2 equals to V2 by RF. Since V1 is equal to V2, I can draw this equation. I can rewrite this equation as I2 is equal to V1 by RF, right? Now coming to the biasing currents. What are the biasing currents we have? IB minus as well as IB plus. IB minus is given by initially I1 plus I2. That is IB minus is equals to, one can draw this as I1 plus I2, right? So if you substitute the values of I1 and I2 already, which is already defined here. So what we said, I1 equals to V1 by RF and V1 by R1. I1 is V1 by R1 and I2 is given by V2 by RF initially, and later with the assumption of VA equal to 0, we said I2 equals to V1 by RF. So what we will get here out of this one, V1 by, if you take both terms having V1, that is V1 by R1 I have plus V1 by RF I have. I can easily take V1 as common and I can say V1 into V1 by R1 plus 1 by RF I can say. So take the LCM out of it. So what will you get here? V1 into R1 plus RF by R1 RF. So this is the expression you can obtain for the base current IB minus at the inverting terminal, right? And from this, one can define the expression for compensating resistance. I said this is a design value. Compensating resistance is a design value. how much value I need to insert, as how much resistance I need to consider for compensating resistance. This is given by the parallel combination of the two resistors. What are the two resistors? The R1 as well as the feedback resistance RF. So the compensating resistance RF is given by, so what we said here, R1 parallel to RF. How we are getting this one? Look here, we said IB plus. What is IB plus? IB plus is equal to V1 by, we said IB plus is equals to V1 by the compensating resistance R, right? So in the ideal situation, what we said, IB plus is equal to IB minus. I have got an expression for IB minus. What is the expression for IB minus? It is given by V1 into R1 plus RF by R1 into RF. And IB minus is given by V1 by R compensating resistance. Equating these two, you can cancel out your V1 and we are getting the expression for the compensating resistance. What is the expression for compensating resistance? Here we are getting, after equating, see this is the case assuming VA equal to 0. VA equal to 0 across the inverting terminals of the operational amplifier. So what we have now, V1 is cancelled out and we left with R1 plus RF. By R1 RF is equals to 1 by compensating resistance R. So what is this expression? If you remember, this forms the parallel combination of R1 and RF. This gives the parallel combination of R1 as well as RF. So we can draw this expression. So if what is the design value of the compensating resistance? The design value of our compensating resistance here is the parallel combination of the two resistors. The two resistors RC is equals to R1 parallels to RF. So this is happened with an assumption of VA equal to 0, right? And now if we move to the next parameter, that is offset current. So which is called input offset current. So let us see what is it actually. If the bias currents IB plus and IB minus are equivalent, let us say that is IB plus and IB minus both are equivalent, bias current correction will function, thus identical input transistors are not possible. There will be some inevitable signal because of some minor variations, nothing but the offset current. So what is IOS here? IOS is generally the combination of both IB plus minus IB minus offsetting current, input offset current, IOS. The current IOS for BGT is generally stated as 200 nanoamperes, some general approximate value, where for FET it is going to be 10 pico amperes, very small in fact. So for transistor it is nanoamperes and for FET it is pico amperes. When VA equal to 0, again the condition is when VA equal to 0, offset current will still result in an input voltage even with bias current adjustments. Offset current will still be available. So what we said for the transistor, it purely depends on how you are going to design the differential amplifier. If you design that using the FET, the approximate value is 200 nanoamperes. If you design the same using FET, there will be an approximate value of 10 picoamperes, right? See, we have input, let us say V1 is equals to, we define IB plus. What we said about the IB plus, it is given by the V1 by the compensating resistance. And you can get the expression for a V1, that is V1 is equal to IB plus into, that is IB, the biasing current across the non-inverting terminal, into the compensating resistance. And we have the general value for I1, that is I1 equal to V1 by R1. So what about these two now? So from these two expressions, one can write I2. What is I2 now? You can say I2 as IB minus I1. So what we are going to say here? I2 is equals to IB minus I1. So you know about the currents I1 and I2, which are present across the two terminals of your operational amplifier, right? And from here you can say V0. V0 is nothing but output voltage. You can easily say that I2 RF minus V1, right? So keeping the feedback resistance low, right, the offset current may be reduced. See, it is certain, the value is still available, it is inevitable, we cannot overcome that. How to overcome that? One kind of solution here is keeping the feedback resistance low, that is RF, whatever we said, no, the feedback resistance RF low. One can expect the offset current may be reduced, right? And unfortunately, R1 needs to be kept big in order to get high input impedance. So we, in the circuit, we have both R1 as well as RF in the op-amp circuit. We have both R1 as well as RF, where R1 is responsible for maintaining the large value of the input impedance. If you make R1 as small, the consequence is you are going to see the effect. You are going to see the effect in your input impedance, right? The feedback resistor RF needs to be high if R1 is large. So this is the relation one can say. If R1 is high, RF is supposed to be high. But what is required here? In order to reduce the offset current, we need to maintain the low feedback resistance. We need to maintain the low feedback resistance so that you can reduce this offset current to some level. So this is what the effect of one parameter on other, one component on other, right? I cannot reduce the R1. If I reduce R1, what will happen? The input impedance Zi may drop. So if I reduce R1, the first effect is on input impedance Zi. So I need to maintain this R1 as possible, as high as possible. If I want to maintain R1 as high, the immediate effect is on RF. RF should be high. RF should be high, right? To achieve a justifiable profitable, the T feedback network, we are coming up with this kind of solution, that is the T feedback network is an effective remedy to overcome this sort of issue, this kind of issue, right? So this will enable a high feedback resistance while maintaining low ground resistance. So you are going to see a new kind of circuit here. We are going to see a new circuit here. So what is it? We are going to introduce a network so that will maintain both R1 and RF justification with a justified value to overcome the problem of offset current, right? And now if you observe the total value, right? So what we said, one kind of approach is coming up with a T feedback network that will maintain a reasonable values for R1 RF as well as your offset current. So despite the adoption of this kind of compensation, it is observed that the output voltage V0 with VA equal to 0 may not be 0. So what is the meaning here? If I say VA equal to 0, what is the ideal situation? V0 should be 0. But still, this may not be 0. It is the effect of your offset current. Okay. As a result of inherent imbalance inside the op-amp, this occurs and the output V0 may need to be set to be 0. So this is a test case. What is how to test the circuit? Make VA equal to 0. Make VA equal to 0 and get the value of V0 also 0. If this is true, then everything is fine. Generally, this will not be true because of the internal imbalance within the operational amplifier. Now, this is the challenge here, right? Input offset voltage, the name of this voltage. So, what we are going to say, which is going to dominate here, is the offset voltage. This is the input voltage that must be provided in order to set the output voltage to 0. That is called the offset voltage. So look at the name offset. So who is going to set off output voltage to be 0? To achieve this, maintain this at a satisfactory level. So what we are going to say, input offset voltage, generally denoted as VOS, input offset voltage. This is the voltage that must be provided in order to set the output voltage to 0. That is the purpose of it. So look at the circuit here. You can observe this offset voltage provided to the non-inverting terminal here. So this will ensure the output voltage V0 to 0, right? So here you can say VA equal to 0. This time we are talking with respect to the non-inverting terminal, right? And so let us talk about the VOT, that is the total offset voltage. What is the total offset voltage? It may be different. The total offset voltage may be different from that of the output offset voltage brought on by the input bias currents and offset voltage alone. See, all these parameters are interconnected. That's what I want to summarize. So under DC characteristics of operational amplifier, we need to talk about the biasing currents as well as offset parameters, biasing parameters as well as offset parameters. All these are interconnected together. They will meet at a point that is called the test case. What is the test case? When VI is equal to 0, V0 should be 0, right? This is what we need to achieve. Because of IB and VOS, it might be either positive effect on the ground. There might be some positive effects, and many op amps contain offset compensation pins. Additional pins are available for compensation, right? To cancel the offset parameters, right? So these pins are between 1 and 5. The offset null will be there. So you can see when we present the pin configuration for IC741, you can see offset null, right? We will insert a 10K potentiometer, and the placement of these wipes, right? These wipes are usually connected to the negative supply of pin 4, negative biasing parameter, negative biasing voltage, and the placement of the wipes is changed to eliminate the offset voltage. So what we are going to talk about here? So on which we are going to focus? It is nothing but the offset null. So if you observe the op amp, what we have seen, so you may notice there are only 5 pins. So if I say this is my operational amplifier, you can see there are only 5 pins. What are they? One is the 2 inputs and 2 bias and 1 output. And now there is another important pin that will address all these kind of issues. Nothing but offset null. Nothing but the offset null. So this is about your, so this is what the compensating network, what we have said, right? So these are the characteristics, DC characteristics of different operational amplifier. The key focus is on input bias currents as well as the offset voltages. So bias currents are nothing but IB plus and IB minus, and offset voltage is nothing but VOS. So you need to highlight your discussion for DC characteristics, keeping these 3 components or parameters in mind, how they are going to occur, how they are going to affect one another. how they are going to impact your output voltage, V out, right? So these are the three parameters that talks about the DC characteristics of operational amplifier, are basically called as DC components, bias currents as well as the offset voltage. So with this we conclude this lecture, and in the next class we will continue the discussion on operational amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.